Is a minimal cover in functional dependencies and what is the equivalence. So initially we'll start the topic which is equivalence, how to find equivalence in functional dependencies. Equivalence in functional dependencies. Okay, so what is an equivalence? Let us first define it formally. No, so two sets of functional dependencies, f and g are said to be equivalent 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 if and only if f closure is equal to g closure. Hence equivalence means that every functional dependencies in f can be inferred using g, and every functional dependency in g can be inferred using f, that is f is equal to g if and only if both f covers g and g covers f, and g covers f holds. If f covers g and g covers f hold. So this is important statement. Okay, so let me tell you, explain it to you with a simple example here what I am teaching here. So let us take this example. Assuming that we have two sets of functional dependency, the first set functional dependency f is a determines c, ac determines d, and e determines ad, and e determines h. This is the first set. And second set is g, which is a determines cd and e determines ah. We have these two sets. Okay, now they are asking, is these two functional dependency sets are equivalent or not? Okay, see, what do you mean by f covers g? Here there's a statement which is saying f covers g. What do you mean by f covers g? When can you say f covers g? If every functional dependency in g can also be determined by the functional dependencies in f, then you can say f covers g. Or you can say, if you cannot find a functional dependency in g which cannot be determined in f, then it is f covers g. Or there's one more way of saying, there's nothing is g in g which is present which cannot be determined in f. Okay, in the same way, if I say g covers f, that means everything which is present in g can also be determined using f. Okay, so f covers g can be denoted like this: f covers g and g covers f. This can also be denoted like this. Okay, that means when I'm saying f covers g, that means if this is the set which is denoting f, then this is the set which is denoting g. When I'm saying g covers f, that means if this is the set which is denoting f, then this is the set which is denoting g. That means every functional dependency which is denoted in f can also be denoted in g. Here every function, or you can say every functional dependency, g covers, I'm so sorry, I have to write g here and I have to write f here. So that means every functional dependency which is denoted in f can also be denoted in g. Yet every functional dependency which is denoted in g can also be denoted in f. Then if both of them holds, that means we can say f is equal to g. Now here in this example, can you find a functional dependency in f? The shortcut way of solving. Can you find in functional dependency in f which cannot be inferred or derived in g? Can you find a functional dependency in f which cannot be inferred or derived from g, or can you find a functional dependency in G which cannot which cannot be inferred or derived from f, then if you can find if you cannot find cannot if sorry if you can find then f and g are not equivalent, then f and g are not equivalent. But if you cannot find, then you can say f and g are equivalent. Now you can see this something this functional dependency in G, that is A derives CD, this can be broken down to two parts, that is A derives C and A derives D. So A derives C is already present in F, right? And A derives D is not present in F, right? A derives D is not present in F. Then how can you say this A derives D is only present in G but not in F? That the easiest way of doing this is, because if A derives D is by looks, or you can say exactly the same statement is not present here, but how can you say that F cannot derive this? Take A closure in F. If in A closure we have D, then you can say this A derives D is also present in F. So if you take A closure in F, so you can see from A we can derive C, from AC we can derive D. Now because there is a D here, therefore this functional dependency can also be determined in F. Okay, this, or you can say this is also present in F. Now here in the same way, here we have E derives AH. So if you have E derives A, we can write it as E derives H, right? So E derives A is also present in here, because if I can write it as E derives A and E derives D, right? E derives A is present here, right? E derives H is also present here, but E derives D is present in this above functional dependency, but it is not present here. E derives D. So how can you say E derives D is also present here? Take E closure for this functional dependency G. That means for G, take E closure. If E closure contains D, then obviously E derives D can also be determined in G. So E closure can be E, A, H, and with the help of A I can derive CD. Therefore in E closure we have D, therefore this functional dependency is also covered in G. Right, now the only thing which is remaining is AC derives T. AC derives T, which is present in F but it is not present in G. So if you take AC closure in G, then what are the things you can identify? AC closure contains A, C, D, right? So ACD is there. So because ACD contains D, hence this AC derives D can also be covered in G. So there is nothing which is present in F but not present in G, and there is nothing which is present in G but not present in F. Therefore we can say F and G are equivalent. F and G are equivalent. So let us take a few more examples of equivalence. Assuming that we are having the following functional dependencies and we want to identify whether they are equivalent or not. So assuming the functional dependency F is A derives B, B derives C, and C derives D, and the functional dependency in G, they are A derives BC and C derives D. So these are the two sets of functional dependencies which are given, and we have to identify whether F is equivalent to G or not. Whether F is equivalent to G or not. Okay, for this purposes, first of all try to identify, is there anything which is present in F but not in G, or is there anything which is present in G but not in F. So you can see this in F we have, see in G this functional dependency can be broken down to two parts, that is A derives B and A derives C. But you can see A derives C is not present in F, and in this case we have B derives C, and this B derives C is not present in G. So let us do one thing. If you want to make sure whether this is present or not, do one thing, take A closure in F. So if you take A closure in F, you can get A derives AB, and with the help of B I can derive C, and with the help of C I can derive D. Therefore A derives, this C is already present, therefore A can derive C, and you can clearly see it is the transitivity property, that means A derives B, B derives C, therefore obviously A can derive C. So this is present in F. And you can say in case of F, B drive C is present but it is not given in G. So if you take in G, if you take B closure, then you can identify we have B, and see we have B, but we cannot derive C in any case. We cannot derive C in any case. Therefore this is a functional dependency which is present in F but not in G. So B drives G is present in F but not in G, So this B drives G is a functional dependency which is saying that F and G are not equivalent. F and G are not equivalent. F and G are not equivalent in this case. Okay, right? If F and G are not equivalent, can you say that F covers G? Can you say F covers G, right? So you can see everything which is present is in G is also present in F, but in F there's something extra which is also present. Therefore I can say F covers G. F covers G. But can you say G covers F? G covers F? No. Why? Because there's nothing in G which is not present in F, therefore G does not cover F, because everything which is present in G is also present in F. So G does not cover F. G does not cover F. That is why F and G are not equivalent. F and G are not equivalent. Okay, now let us take the next example. The functional dependencies which are given are F A derives B, AB derives C, and D derives AC, and D derives E. This is the first set of functional dependency, and this is G, which is A derives BC and D derives AB. These are the two sets of functional dependencies which are given. Okay, now if I take F closure, see, we have to identify something which is present in F but not in G, which is present in G but not in F. Or you can say, first of all we can identify whether F covers G or not, and then we can identify whether G covers F or not. G covers F or not. So to see if F covers G or not, that means we have to identify anything in G which is not present in F. So this G can be broken down like this. A can derive B, A can derive C, D can derive A, and D can derive B, right? See, if you have AB can derive C, then you cannot break it as A can derive C and A can derive B, B can derive C. You cannot break it like this, right? But if you have A can derive BC, then you can break it like this: A can derive B as well as A can derive C. You can break it like this. This is allowed, but this is not allowed. Okay. So here A can derive B is already present in F. Directly it is present, so it is covered. And if you say here we have D drives AC, so D drives A is directly present there, because this can be written as okay, let me do one thing. Let me expand this one also. A drives B, AB drives C, D drives A, D drives C, and D drives E. So you can clearly see this thing is directly present, this thing is directly present. Okay, but we do not have A drives C here, and we don't have D drive. This is for the F, and this is for G, right? If I say F covers G, that means we have to find something in G which is not there in F. So these two things are not there in F, that is A drives C. So if you take F, then if you in the F you can take A closure. Let us see what are the things you can identify, or let me write in. If you take A closure in F, then A closure can identify A. With the help of A, I can identify B. With the help of AB, I can identify C, but I cannot identify anything else, right? I cannot identify anything else. Therefore, A closure is containing C. Hence, this is present in F. Okay. Now let us see if we have D drives B, which is present in F or not. That means in case of F, or right. So. Okay, this is present in F or not, right? So if you take F, D drives B, D closure in F, then you can get D. With the help of D, you can identify AC, and with the help of A, you can identify B, right? Therefore, because we have B here, therefore D drives B can also be set. So you can say here in the case, F covers G holds. F covers G holds. Now let us see if G covers F hold or not. That means, can you identify something in F which is not present in G? Can you identify something in F which is not present in G? So take these examples. We have AB. This is not present in G directly, and this is not present in G directly, and this is not present in G directly. So if you take this one, so AB. So if you take AB closure in G, let us see if we can C or not. With the help of A, B, we can identify C, right? So this is C is already present, so this is also covered. This is also covered. Now let us see this one. That means, can you get, if you take D closure in G, can you get C or not? If you take D closure, you can see we get D, A, B, and with the help of A, you can get C. Therefore, this is also covered. Let us see if can I get D drives E, but you can clearly see in any of the functional dependencies in G, we do not have any mentions of E. So therefore, this is not present. This is not present in F. This is not this is not present in G. This is not present in G, but present in Z, but present in F. Hence we can say that G does not cover F, so this does not hold, right? So graphically you can say if this is representing F and this is representing G, then this does hold, and if this is representing G and this is representing F, this does not hold, right? Therefore F and G are not equivalent. F and G are not equivalent for this particular case. Okay, now let us take the next example. Assuming that the functional dependencies which are given are like this: F is A derives B, B derives C, and C derives A, and G is saying A derives BC and B derives A and C derives A. These are the two functional dependencies which are given. So let us see if F covers G or not and G covers F or not. Okay, so these functional dependencies, the only thing which can be broken down here is this one, that is A derives B and A derives C. So A derives B is also present here, okay, and A drives C is also present here. Why? Because A can drive B, B can drive C, therefore A can drive C. So this is transitive, it is also present here. If I say B drives A is present here or not, that means if I take B closure, then I can find B, C, A, because we can identify B, C, A, therefore this is also covered there. And if I take C closure here, then I can identify A, B, C further, therefore this is also present here. So you can see G covers F. In the same way, you can take examples where F covers G, because in case of F, even if you take A closure, then you can identify A, B, C, right? So here F covers G as well as G covers F, F covers G as well as G covers F, hence F and G are equivalent. Okay, now in the next video, let us identify how to identify the minimal set or minimal cover in functional dependencies. And what is a minimal cover is that given a very big set of functional dependencies, can you minimize it to get a smaller set? Because if we can get a smaller set, then it will make things very simple for us. It will make things very easy for us, and to write the functional dependencies as well as to understand what is going on. Okay.